Welcome to a session on mean free path. In this session, we will be seeing the derivation of a mean free path and also the effect of temperature and pressure on mean free path. Now, let us move on to the contents, that is, we will be seeing mean free path and effect of temperature and pressure on mean free path. Okay. Now, we all know that from kinetic theory of gases, the molecules within a container will be in a state of rapid random motion in which they collide with each other and also with the walls of the container. So, just to show that I have taken a picture from the internet and you can see that, see here this is the start point of a gas molecule. It is finally reaches at this point, that is I have written it as finish. This is the starting point and this is the finishing point. Now, in the movement of the gas molecule, you can see that, see there are a number of short straight line motions, okay, and after each distance you can see that it is changing its direction of motion, okay. Now, if the gas molecule, if we are having only one gas molecule, only single gas molecule, and this gas molecule is kept in an evacuated, that is vacuum. Okay, so this is a vacuum. Now, this gas molecule can move straight towards, I mean, suppose it is supposed to reach here. Okay, so it moves in a straight line motion. Why? Because there is no collision between the molecules there. There are no other molecule. We are having a single molecule over here, and it is vacuum, means there is no medium. Medium in the sense it can be either air or whatever it is. There are no molecules of the medium which will be colliding with the gas molecules to divert its path. So, neither the gas molecules or the medium reverts its path. Okay. Now, in this case you are taking a gas, there are many molecules. When the gas moves to this point, it gets collided either with the medium or with the same molecules of the gas and its direction of motion is changed. So, it moves to this. Again there is a collision, again it moves in another direction in a zigzag manner, that is we call it as a rapid random motion, and finally reaches the point, the finish point. Okay. So, because of the collision it changes its direction of motion and also in some cases it changes its velocity, because we know that even the collisions are elastic, there can be changes in kinetic energy. So, when a gas moves, you can see that here it has travelled so much, this much distance, and this it is bit shorter. So, you have a different number of distances between the collisions. So, what we are going to do is, we are going to find out the average distance a molecule can travel. Okay, it is an average distance, it is not exactly always after that distance it collides with another molecule, it is an average, it may vary to some extent. So, the average distance travelled by a molecule to in between two collisions, that is it collides with one molecule or it is any other molecule, either the same gas or the medium, then it travels a certain distance and then undergoes another collision. So, the travel distance between two successive collisions, and this is known as mean free path. That means from the name itself, mean stands for average, because it is not exact value, because it will be slightly varying. Now, free path means, that is the molecule is travelling free and it does not undergo any collisions. So, that is known as free path. Okay. Now, mean free path It is the average distance travelled by a molecule between two successive collisions. It is known as mean free path and it is denoted by the Greek alphabet lambda. Lambda is equal to v by z, where v is the average velocity and z is the collision number. Now, velocity means we know that it is the distance travelled in unit time, that is distance travelled in unit time. Collision number means it is a number of collisions, in unit time per unit volume. Okay, whatever it is, we can consider that it is number of collisions in unit time, and this is the velocity means distance travelled in unit time. Unit time. Okay, so this is the distance travelled and this is the number of collisions per unit time, both in unit time. So, distance travelled divided by number of collisions, of course, that will be giving the distance travelled without any collisions, that is V divided by Z. And we all know that Z, the collision number, is given by the expression Z is equal to root 2 pi V sigma square rho. V is the average velocity which we have already mentioned, and sigma, what is that? Sigma is the collision diameter, and rho is known as number density. Number density means instead of mass we will be taking number per unit volume. So, this is known as number density. Now, substituting this in this above equation, that is lambda is equal to V by Z, we will put it as lambda equals V by Z. Instead of Z, I substitute root 2 pi V sigma square rho. V and V will get cancelled. You will get the expression as 1 by root 2 pi sigma square into rho. So, this is one of the expression for mean free path. Okay. That is lambda equals 1 by root 2 pi sigma square rho. Okay. Now, here you can see that as the collision diameter is at the denominator, okay, if collision diameter increases, what will happen? This value decreases. Whatever number density increases, again the mean free path decreases. That is, when collision diameter is greater, is a bigger molecule, okay, so that will be easily colliding by the nearby molecules. So, when when collision diameter increases, lambda decreases, that is the space to move freely without any collision decreases. Now, next is number density, or you can say it represents number of molecules per unit volume. Now, when that increases, again mean free path decreases, that is number density means it is crowded. So, again the distance moved without collision, again that will keep on decreasing. Okay. So, this is one expression, you will have to by heart it because you may get problems based on these equations. Now, let us see what is the effect of temperature and pressure on mean free path. So, we will take the expression again, lambda is equal to 1 by root 2 pi sigma square rho. Now, what I am going to do is, here we do not have any term representing temperature and pressure, both are not there. So, we will have to do some substitutions. So, for that what I am going to do is, I am going to take ideal gas equation for n moles. PV equals nRT. PV equals nRT, where P stands for pressure, V is the volume, N is the number of moles, R is universal gas constant per mole, and T is the temperature in Kelvin scale. Now, what I am going to do is, I am going to take V to this side. So, the expression becomes P is equal to N by V RT. Okay. Actually, I am going to make a substitution for the number density. Okay, that is what my aim is. Here N by V, this is number of moles and not molecules. Number density is number of molecules per unit volume. Here it is, this is number of moles, N is number of moles, do not forget. Not molecules. Okay. Now, what I am going to do is, I will retain it here N by V, and to the other side I am going to take both R and T. So, the expression will be N by V is equal to, when this goes there, it will be in the denominator, P by RT. Okay. Now, what I am going to do is, I want the number of molecules, not number of moles. So, since this is an equation, I will multiply both sides with N naught or N0. What is N0? That is the Avogadro's number, which is equal to 6.022 into 10 to the power 23. Okay. So, I am going to multiply both sides, that is N0 into small n by V is equal to N0 P by RT. Now, here if you note, this is number of moles. 1 mole contains 6.022 into 10 to the power 23 molecules. Multiplying it with number of moles, here this factor, that is N0 N, is a total number of molecules. N0 N, total number of molecules. Okay. And V is the volume. So, this term now becomes number density. It is the total number of molecules per unit volume. So, I can substitute this as N0 N by V can be taken as number density rho. So, let me substitute it over there. You can put it as rho equals N0 P by RT. Next, what I am going to do is, I am going to take this N0 to the denominator. To the denominator means, when it comes over here, it becomes the denominator of the denominator. So, rho is equal to P by R by N0 into T. Now, R is universal gas constant for 1 mole. R is universal gas constant for 1 mole. Gas constant per mole, that is for 1 mole. Okay. Now, this R value divided by number of molecules in 1 mole. The value of R divided by number of molecules in 1 mole will give you, that is R by N0. What is that? It is a gas constant. Here R is for 1 mole divided by number of molecules in 1 mole will give you gas constant value per molecule. Got it? And this value is represented by a constant K known as Boltzmann constant. I will make it clear. R is a universal gas constant for 1 mole, it is known as R, and the gas constant for 1 molecule is known as Boltzmann constant, it is represented by the K, letter K. Okay, now I am going to substitute that over there. Rho is equal to P by K into T. Okay. Now, here one more point, that is we have been seeing that is the mean free path lambda is equal to 1 by square root of 2 pi sigma square rho, where rho is the number density, and for rho we have found a substitution. Okay. So, I am going to substitute that lambda equals 1 by root 2 pi sigma square, and instead of rho, it is rho over here, and instead of rho I will put it as P by Kt. Okay. Now, just taking Kt to the numerator, I will have Kt in the numerator divided by root 2 pi sigma square, P is retained here, and this is an expression for mean free path in terms of pressure and temperature. So, this is one more expression you will have to by heart it, because in problems when they give the temperature and pressure you will have to use this expression, and if you are given number density and collision diameter you can go for the former one. Okay. So, this is the expression lambda equals Kt by root 2 pi sigma square into P. That is what we have derived. And in this derivation, please note that we have started with ideal gas equation for n moles, and we derived an expression for number density as P by Kt, and we have substituted that in the mean free path expression, and finally we got this expression lambda equals Kt by root 2 pi sigma square P. Now, let us see how does mean free path change with temperature and pressure. Now, we are going to see the effect. Here sigma, this is one of the variable, K is a constant, Boltzmann constant, one is sigma, temperature and pressure are the variables, temperature and pressure. Sigma is the collision diameter. And if you take a molecule, the collision diameter does not vary with temperature and pressure, because we consider the molecules to be hard spheres. So, change in temperature or pressure will not affect the collision diameter. So, I am going to keep collision diameter also as a constant. Now, what are the variables now? Only temperature and pressure. Since temperature is in the numerator, if temperature increases, when temperature increases, what will happen to mean free path? It increases, because when temperature increases they will be moving apart, and therefore mean free path also increases. What about pressure? When pressure increases, and by the way, when temperature is increased, P is maintained constant. Okay, here temperature is maintained constant. When P increases, it is in the denominator, and therefore the lambda value decreases. So, this is the effect of temperature and pressure on mean free path. Now, let us move for a problem. Calculate the mean free path of a gas at STP, where the collision diameter is 2 into 10 to the power minus 10 meters. The collision diameter, the data sigma is equal to collision diameter represented by the letter sigma is equal to 2 into 10 to the power minus 10 meters, and they have given nothing else, because we know since it is STP, the temperature will be 273 and pressure will be 1.01325 into 10 to the power 5 newtons per meter square, that we have to know it by heart, or you can have it from the Clark's table. The expression for mean free path lambda is equal to 1 by square root of 2 into pi sigma square rho. But this equation cannot be used, because why is it so? What we have is only the collision diameter. Okay. So, we will have to go for another expression, that is lambda is equal to kT into root 2 pi sigma square P, where P is the pressure. Okay. Now, let us move on. That is pressure we have, temperature we have. In this we do not have all the details given here. Now, we do not have the value of K, which is Boltzmann constant, but we know that it is universal gas constant by Avogadro number, and therefore, that is 8.314, that is a universal gas constant divided by 6.022 into 10 to the power 23. Now, we have all the data. Now, you can find out the mean free path. Now, substituting, we get K, instead of K I am going to put it as 8.314 whole divided by 6.022 into 10 to the power 23. I am not writing the units, because we know that this is the distance and therefore, that will be meters. Into temperature, temperature we know, because it is said that it is STP 273. Okay. Now, we have here root 2 into root 2 into pi, we know that it is 3.14 into sigma square. Sigma square, sigma is 2 into 10 to the power minus 10 square into P, pressure is equal to 1.01325 into 10 to the power 5. Okay. Using a scientific calculator, if you solve for it, you will get the answer as 2.094 into 10 to the power minus 7 meters. So, that is the answer of lambda. And one more problem. Calculate the collision number, collision frequency and the mean free path of oxygen at 298 Kelvin and 1 bar, given the collision diameter equals 357 picometers. Temperature T is equal to 298 Kelvin, pressure is equal to 1 bar, which is equal to actually 1.013 is there. They have approximated as 1 into 10 to the power 5 newtons per meter square. Sigma is 357 picometers, that means into 10 to the power minus 12 meters. So, we will see one by one. The collision number Z is given by the expression root 2 pi V sigma square rho. You do not have number density here. you do not have the average velocity, these two are not provided. So, number density is equal to, since it is for, we will consider as 1 mole, it is N0 by V. In 1 mole you will have N0 divided by V. Now, we know that PV is equal to RT and V is equal to RT by P. V is equal to RT by V. So, here I can substitute for V as rho equals N0 by RT by P, and this P goes to the numerator and you will get it as rho equals P N0 by RT. Now, all these are known values because pressure is given. Now, you can solve for number density as 1 into 10 to the power 5, that is the pressure, 6.022 into 10 to the power 23, that is Avogadro number, divided by 8.314 into temperature is 298 Kelvin, and solving you will get the answer as 2.431 into 10 to the power 25 per meter cube. This will be the number density, that is number per volume. Now, next is, now you have got the value of rho, number density. Next we have to find out the average velocity. For that we know that V is equal to square root of 8 RT by pi m. Okay. Since it is oxygen, m will be equal to 32 into 10 to the power minus 3 kilogram per mole. N0 it is given here, R is given here, the value of pi is given here. Now, we will find out the value of V. 8 into 8.314 into temperature was 298. Let me confirm. Yes, it is 298. Whole divided by, I will put it here, T is equal to 298 Kelvin. Whole divided by pi, that is 3.14, and molecular mass of oxygen, that is 32 into 10 to the power minus 3. Okay. Now, solving you will get, since this is the velocity, I am not going for taking the units, you can do it yourself. You will get it as 444.13 meters per second. This will be the average velocity. Now, we have all the values. Now, let us calculate the value of Z. Z is given by the expression root 2 pi V sigma square rho. Okay, the values are there. V, the average velocity we have already calculated, V is equal to 444.13 meters per second inverse. Sigma is equal to 357 into 10 to the power minus 12 meters, and rho is equal to 2.431 into 10 to the power 25 per meter cube. Now, we can calculate Z. Z is equal to root 2 into pi 3.14 into V 444.13 multiplied by sigma square. Sigma is 357 into 10 to the power minus 12, and see that is square, into rho. Rho is 2.431 into 10 to the power 25. Now, using a scientific calculator, you can solve it. You will get the answer as 6.1096 into 10 to the power 9 per second inverse. So, that is the answer. Now, let us see what is collision frequency. Collision frequency, that is Z11, because both are same, we do not have a different atoms, is given by the expression 1 by root 2 into pi v sigma square rho square. You have all the values, you can do like that. Or if we compare this with the expression of Z, Z and Z11, you can see that this is an expression, that is Z11, that is what we have to find out, and Z11 is Z into rho by 2, because you are having an additional, this is Z, that is rho square. So, you should multiply it with one more rho, and then, so that becomes, and here we are having root 2 in the numerator. So, if I divide it by 2, it becomes root 2 in the denominator. So, we can solve it easily. The value of Z is known, rho is known. So, you can easily find out Z11, or it is also known as ZII, to show that it is a similar, it is between similar atoms. 6.1096 into 10 to the power 9 second inverse into rho. Rho is 2.431 into 10 to the power 25 meter raised to minus 3 whole divided by 2. Okay. Now, if you solve for it, you will get it as ZII is equal to 7.42 into 10 to the power 34 meter raised to minus 3 second raised to minus 1, that is these two units, and that is the answer. Now, the last one is mean free path. Mean free path, actually the expression is 1 by square root of 2 pi sigma square rho, or you can say that average velocity by collision number, and it is actually from this equation we have reached this equation. Since we have calculated average velocity and collision number, you can substitute that and find out the value of mean free path easily. That is, we have found out the average velocity as 444.13. 444.13 is the average velocity, and divided by Z. Z we have calculated as 6.1096 0.1096 into 10 to the power 9. Substituting that, you can calculate and you will get the answer as 7.2694 into 10 to the power minus 8 meters. So, better if we have found out these two, it is better you can calculate the value of mean free path easily. Now, to conclude, we have been seeing mean free path lambda equals 1 by square root of 2 pi sigma square rho, and mean free path is a distance travelled, it is not for all the collisions. So, we can call it as the average distance travelled between two successive collisions. And we have found out two expressions, one in terms of number density and other one in terms of pressure and temperature. Okay. In this case, you can say or express the change in mean free path with respect to temperature and pressure, and it has been found that as temperature increases, mean free path increases, and when pressure increases, the mean free path decreases. Okay. The effect of temperature and pressure on mean free path is expressed or explained on the basis of this equation. Otherwise, the mean free path is considered as lambda equals 1 by root 2 pi sigma square rho. Thank you, and that is all for today.